A fully loaded container ship is moving at about 20 knots when the order comes from the bridge. Stop the ship. Sounds simple, right? But there is no brake pedal, no brake pad, no giant disc under the deck. Nothing you would call a brake. So how do you stop something this big? The answer is strange because ships do not stop like cars. They use water, propellers, and a plan that starts miles before the dock comes into view. To see how this works, we need to start with the real problem. It is inertia. In simple terms, inertia means something moving wants to keep moving. A bike does it, a train does it. Now, scale that up to a steel box as long as several city blocks, packed with cargo, moving through water. Once that ship is going, it does not just stop because someone says, stop. That is why giant ships look calm from far away. They seem slow, they glide. But hidden logic says the opposite. They are carrying a huge amount of motion, and that motion has to go somewhere first. And water only helps so much. At high speed, the hull and propeller do feel a lot of drag. That drag starts taking energy out of the ship right away. But it is spread over a huge mass, so the slowdown still feels lazy. Then, at lower speed, the problem gets worse in a different way. The ship has less water flow over the rudder and less steering response, so it can become harder to control at the exact moment you need precise movement. That is the part most people miss. A full container ship at around 20 knots can need roughly 3 to 5 miles and up to 15 minutes to come to a full stop. You give the stop command here, and the ship may not be fully stopped until miles later. That is not bad design. That is physics. So why not just add brakes? Because a ship is not rolling on tires. A car brake clamps a wheel, and the tire pushes on the road. A ship has no road. It has water, and water slips away. A brake big enough to stop a giant ship directly would have to handle huge force and huge heat. It would be heavy, bulky, and not very useful. So engineers thought backwards. If water is what the ship moves through, then water has to help stop it. And that brings us to the core mechanism. Ships do not stop by grabbing the hull. They stop by changing what the propeller does to the water. If you like seeing how big machines really work, hit subscribe now, because in the next part, we are going inside the propeller hub and the pod system that actually slows the ship down. Let's strip away the casing and look at the first system, the controllable pitch propeller. A controllable pitch propeller is a propeller whose blades can twist while the whole propeller keeps spinning. That is the clever part. The engine does not always need to reverse. The blades change angle instead. Think of each blade like your hand out of a car window. Tilt your hand one way and the force goes one way. Tilt it the other way and the force flips. A controllable pitch propeller does the same thing in water. Inside the hub, hydraulic oil moves a piston. That piston slides back and forth. Then a yoke, or crank-like link, turns that straight motion into blade rotation. All the blades twist together in sync. When the blades angle for a head thrust, they push water one way and drive the ship forward. Flatten them, and thrust drops towards zero. Twist them past neutral, and they create a stern thrust. Same spinning shaft, same engine speed, but the force flips direction. That change can happen in roughly 15 to 40 seconds. For a ship, that is fast. It means the crew can go from pushing ahead to pulling back without waiting for the whole engine to reverse. Now, compare that to a fixed pitch propeller. Its blades stay locked in one shape. If you want reverse thrust, the engine itself has to reverse. That is slower. So, in simple terms, a controllable pitch propeller lets the ship change its mind faster. But there is another system that goes one step further. It is called an azimuthing podded drive, often called an azipod. This is an electric motor inside a pod under the ship. The pod can rotate a full 360 degrees. So there is no long shaft line and no rudder needed behind it. The thrust points where the ship needs it. Imagine a giant underwater fan on a swivel. Turn the fan and the push changes direction. Most azimuthing podded drive systems use a fixed pitch propeller, but the whole pod turns. So if the ship needs to slow down hard, the pod can rotate and point thrust forward. Instead of pushing the ship ahead, it pushes against the ship's motion. This is why ships with azimuthing potted drives can move in ways that look almost unreal. They can turn in tight spaces, they can push sideways, and when it is time to stop, they can aim force exactly where it helps most. Now, what about bow thrusters and stern thrusters? They are not the main brake. They are mostly for fine control when the ship is already moving slowly. The same goes for anchors. Anchors are not brakes. They hold position once most of the ship's motion is gone. If you drop one while the ship is still moving fast, the loads can get extreme and the gear can be damaged. That is because the anchor is really a holding tool, not a stopping tool. The chain, brake, and windlass are built to manage heavy loads in a controlled way. They are not meant to catch a fast-moving ship like a hook in the ground. If you try that, the chain can run out hard, the brake can overload, and the whole system can take a beating. And then there are tugboats. Once the ship has shed most of its speed, tugs help place the hull exactly where it needs to go. At that point, the problem is less about killing speed and more about trimming the last bit of motion so the hull lines up with the berth. So the hidden logic is simple. The ship uses water as resistance, then turns thrust against itself, then uses small control tools to finish the job.
Here is the part that matters most. The real trick is not a magic brake. It is planning. On big ships, the stop starts long before the dock is close. Pilots often board miles out, and from that point, the crew is already working the problem. Speed, draft, wind, current, traffic, and turning room all matter. That is why good ship handling looks almost boring. The crew is not waiting for the last second. They are bleeding off motion a little at a time, using reverse thrust, hull drag, and timing so the ship arrives with almost no extra energy left. But sometimes there is not enough room. If a real emergency happens, the choices get small very fast. Maximum astern thrust. Thrusters where they can help. Tug support if it is close enough. And if none of that is enough, then the goal changes. It is no longer about a perfect stop. It is about the least bad outcome. In some cases, that can mean a controlled grounding. In simple terms, that means choosing where the ship hits instead of letting physics choose for you. Sand or mud in the right place can be better than a bridge, a crowded dock, or another ship. Even modern systems do not erase the scale of the problem. These ships are not machines you slam to a halt. They are machines you manage early. So when the order comes from the bridge to stop the ship, the crew is not reaching for a break. They are starting a chain of moves designed to let physics work for them before physics works against them. So the next time you see a giant ship slide into port, remember this. It started stopping miles before it looked slow. No brake pedal, no giant pads, just water, thrust, drag, and a crew planning far ahead. If you want more simple breakdowns of the hidden logic inside big machines, subscribe now. And share this with someone who still thinks ships stop with a giant handbrake.